Welcome back, Semester Astronomy. It's Mr. Krug for our final section of notes for the school year. This is going to be section 4, Stars and Galaxies, coming at you. And I already recorded a longer version of this for academic astronomy. I thought for a little bit about just using that one, but I thought, no, I'm going to try to do a shorter version for you guys and girls. So I would encourage you to follow along with the PDF of notes that I posted to Google Classroom. And then somewhere during this lecture, you're going to get 10, count them, 10 questions that you're going to answer on Google Classroom as you switch back and forth. I'm also coming at you today from my back porch, so notice the background's a little bit different here. I need to record here so I can watch my girls playing out in the yard and make sure they don't get attacked by a bear or play with any neighbor kids that I might not know. So a little bit of a different background. Okay, so let's go ahead and get started. I'm going to share my screen with you here. So we just got done with the section on our solar system. And so now this is going to be Stars and Galaxies. Okay, should be good to go here. So when I start off this section and we're in class, I usually try to ask students what a star is. And it's actually pretty tough for even adults to define it. Most people know that our sun is a star, and some people know that our sun is a lot like the other stars in the sky, except it's a lot closer to us. So instead of a little pinpoint of light on the sky, it looks like a big yellow ball. But beyond that, people really struggle. Why is our sun so bright? Is it hot like a coal or like an ember in a fire? Could you actually stand on it? Is it gas? Is it liquid? What exactly is it? So this is my homemade definition. A star is a large ball of glowing gas. It's a plasma or a gas, we could say. And it's hot enough to begin a special F word. No, not that F word. This one right here, nuclear fusion. This is what makes stars hot and bright. And we are going to see, everybody, in just a little bit, that fusion is going to be a catalyst of our universe. So let's talk about stars being born. Now, officially, stars are not actually living, breathing entities like you or I. But some astronomers are actually starting to rethink that, and they're actually trying to do some clever experiments and observations to see if there's a chance that stars can actually do decision-making, just like any other sentient being. But that's pretty far out there. We're going to assume for now that stars are not really alive. But throughout this section, we're still going to make them analogous. We're going to make an analogy to them being alive because it'll be easier for us to understand. We're going to talk about stars being born and stars dying out, baby stars, young to middle-aged stars, grandparent stars, the works. So all stars, everybody, whether big or small, all begin the same way, in a molecular cloud of gas and dust. Over here at the left, you can see one of the most famous pictures ever taken by the Hubble Space Telescope. This is called M16, the Eagle Nebula, and it's actually just a little tiny piece of it zoomed in. This is sometimes dubbed the pillars of creation, and you can actually see baby stars or protostars growing off there like olives on the branches of a tree. Now, throughout a star's life, a silly analogy I'm going to be making in this section is a seesaw between two competing forces. On one side of the seesaw, we have gravity. Gravity wants to tip the seesaw its way and crush the star down to nothingness. On the other side, we have star energy. Star energy wants to expand the star really, really big. Now, early in its life, gravity is the big kid on the playground. The seesaw is tilted this way so much because gravity is so strong. Poor little star energy is just up here on the seesaw with its legs kicking helplessly. So gravity starts to scrunch and contract this star smaller and smaller. And as it gets smaller, though, it gets hotter and hotter until, boom, step 3. The star begins fusion at its center, and for the first time, it starts to push out against the ever-present crush of gravity. So the seesaw starts to tilt back until we reach step 4, which is equilibrium. Root word is equal, meaning the same. So here, gravity and star energy perfectly balance out, and this is where most stars will spend their adult lives. So anytime you look at the sun, and obviously don't look right at the sun, it hurts your eyes, but anytime you just kind of like peek up there, it looks like a totally round, smooth yellow ball where nothing is happening. Could not be further from the truth. Every second of every day, our sun is fighting this life and death battle between two forces. And later in this section, we are going to see what finally wins out. So let's talk about that special F word of fusion. This is what is actually happening in our star every second of every day. And this wasn't really known until the 1900s. Before that, astronomers weren't sure if the sun was burning something, if just the pressure from gravity contracting it made it hot. But fusion was the only thing that could work that would explain why our sun is still going strong after about 5 billion years. So every second of every day, our sun is doing this trillions of times a second in its core. It's taking two atoms of hydrogen, atomic number 1, and it's smashing them together to form one atom of helium, atomic number 2. Here's a really good diagram, but it might be labeled in a way that confuses you a little bit. Deuterium and tritium are both isotopes of hydrogen, atomic number 1. Notice they both have one proton because they're both hydrogen. They then smash together to form a helium-4. Helium is atomic number 2, but its mass number is 4. We have 2 protons and 2 neutrons. So 2 plus 3 equals 4. Wait a minute, 2 plus 3 does not equal 4. Notice, teens, we have 1 neutron that gets left out of the party. So then this guy cruises around the core, finds another deuterium, smashes together to form a tritium, finds another deuterium, smashes together, form a helium, on and on and on. This reaction is so prolific, I have read, this is insane, our sun loses anywhere from 20,000 up to 200,000 tons of mass every single second from this reaction. But our sun is massive enough, it's been doing it for 4.5 billion years, it has enough left in the tank to probably do it for another 4 billion more. All right, so let's talk a little bit about the properties of stars. We can see our sun up close, but we also see there's many, many other stars in the sky. And even here from Earth, you can tell that some stars look very differently. So we are going to see that the diversity of stars is greater than that even of the diversity of people on the Earth. They all begin in a very similar way, but then they diversify quickly. So one of the most prominent ways they diversify is through mass. There are stars out there that are up to 2,000 times larger than the sun. These are stars, everybody, that are so large, if you put them in our solar system in place of the sun, they would engulf all the planets out past Mars. And yet on the flip side, there are some stars so small you could fit them in between Altoona and nearby Tyrone, only about 10 miles away in that direction back behind me there. We are going to see that our sun is about average, and a common theme throughout section 4, everybody, our sun is a very average star. We'll learn more about that in a bit. Okay, properties 2 and 3 go together, and that's color and temperature. What that means is the relationship is so consistent, you can always use one to find the other. When you look up at the sky at night, if you can identify a star's color, you automatically have an idea of its temperature. Oops, I just saw my battery is about to run out. 1 minute. All right, sorry about that. Back to the action. If, however, you would know a star's temperature from like a spectral readout, you could infer the color. So notice here, everybody, blue or blue-white are the hottest star colors, followed by white. And then notice once again, our sun is about average. It's yellow, it's right in the middle. And then we have red, orange, and red. Now, throughout this section, I'm going to refer to the orange and red stars as cool, but understand cool is a relative term. It doesn't mean cool like ice cubes or polar bears. Even a cool star is still about 3,000 degrees Celsius. But compared to our sun, and especially the blue and white stars, that's exceptionally cool. Okay, here comes the first sticky wicket, and that's brightness. It would be nice if you could go outside and look up and say, ah, that star is very bright, it must be very big, or that star is very dim, it must be very small. But we're going to see there are so many things that factor into play. Letter A, a star's size. Overall, bigger stars tend to look brighter than smaller stars. Letter B, the actual brightness. Some stars are just inherently brighter than others. Letter C, the color. Did you know that the human eye is a little bit biased? We can see blues and whites, your high frequency colors, better than we can oranges and reds, the lower frequency colors. So our eyes deceive us into thinking that most of the stars in the sky are blue or blue-white, and that's certainly not the case. But finally, everyone, the real monkey wrench here is apparent brightness. This is how bright stars look because of distance. Stars that are very close to the Earth tend to appear brighter than stars which are very, very far away from the Earth. So because of this trickiness, everyone, astronomers use 3 different brightness terms. So the first is actually the one you are already most familiar with. We see this on our star charts. We see this when I used to bring down the lights in the planetarium and put the stars on the sky. You see this every night that you go outside and you look up. This is apparent magnitude. The root word is appear. This is how bright stars appear because they are at different distances from us. So in this diagram here, I made it simple, but you can see the stars that are closest to our little dude or dudette appear brighter than the ones which are farther away. Our next term is called absolute magnitude. I call this like the police lineup of stars because you're hypothetically lining a bunch of stars up beside each other. Here, we take these different distances and we line them up together. The stars which are very close, we pull back. The stars which are very far away, we mathematically pull up close. And then it's a lot easier to compare them. Notice, Astro Teens, I tried to make these diagrams look the same. So up here, notice the stars very close to our person appear bright. The ones farther away appear dim. But now if we look at the second diagram, if we move them all to a standard distance, notice the star that appeared bright was really only bright because it was close to the Earth. Once we moved it back, it was quite dim. Meanwhile, some of the stars that appeared dimmer only looked that way because they were far from the Earth. If we move them to a standard distance, they're a lot brighter. Finally, everybody, the last brightness term is luminosity. Here, you don't factor in distance at all. It's just the size of the star along with its temperature. Okay, to finish up on properties of stars, we have density and we have composition. Like Earth and like most planets and most moons, the density of a star increases towards its center. So the core is the most dense, that's where fusion begins, and then the layers get progressively lighter and less dense as you go. Composition. Stars like our sun are not that big. They will fuse the whole way up to carbon, which is a building block of our bodies, but high mass stars fuse the whole way up to iron. Interestingly, quick aside, the famous and popular astronomer Carl Sagan used to always say that humans are made of the stuff of stars. So think about that. Right now, the carbon that's in your body and the iron that's coursing through your blood long ago was forged in the nuclear furnaces of stars before many of them, boom, supernovaed and then spread that stellar ash through the cosmos. So Sagan was right. We are truly made of the stuff of stars. So the last thing to talk about here for the first part of our lecture, because I think I am, let me see, page 1, page 2, page 3. Let me just double check my questions. This is probably the most awesome diagram in all of astronomy. It is called the Hertzsprung-Russell diagram. So this was actually invented or discovered, well, not discovered, invented by 2 different astronomers. One was named Hertzsprung, one was named Russell. They both happen to be working on the same concept at the same time. And this is kind of cool because rather than just trying to snake each other for credit, which happens way more in the scientific community than you'd think, they both corresponded with each other and said, hey, why don't we just share this idea, which hardly ever happens. And so this became known as the Hertzsprung-Russell or the HR diagram. So what they're doing here, everybody, is they're classifying all stars in the universe according to 2 properties, their temperature and their brightness. So in a way, it looks a lot like an XY diagram you would have in math, but the big difference, take a look at the temperature axis. It actually increases to the left. So the hotter stars are over to the left, the cooler stars are over to the right. Now, a couple differences. Sometimes you'll see an HR diagram and it will show the temperature at the bottom, and it might be in Celsius or Fahrenheit. This one I found online has it in Kelvin. Sometimes it'll show these spectral classes across the top. The spectral classes seem like a silly arrangement of letters. The silly way that astronomers remember this, OBAFGKM, is OB a fine girl kiss me, or OB a fine guy kiss me, OBAFGKM. Finally, if we look over at the brightness axis, here they're showing absolute magnitude. Remember from our star charts, the negative numbers are the brighter stars. So we actually have the brightest stars up at the top, the dimmer ones down at the bottom. I have also seen HR diagrams that will show luminosity over on this axis instead of absolute magnitude. About the only thing you won't see there would be apparent magnitude. Remember, that's when stars are at different distances. And the whole point of this diagram, everybody, is to level the playing field because science likes to make even comparisons. So before we end today, you can see we have 4 main star groups. We have the main sequence, which is the biggest star family in space. And notice our sun is a part of it. Once again, everybody, note that our sun is about average. It's not going to be too hot, not going to be too cool, not going to be too bright, not going to be too dim. It's about average. Across the top, we have the real whoppers of stars, the massive supergiants. Notice the blue ones are going to be very hot and very bright. The red supergiants, though, are going to be very cool and bright because they're in the upper right. Snuggled down below the red supergiants, we have a group called red giants. And we'll see in the next lecture, our own sun will become a red giant someday. They are also cool like red supergiants, but they're not quite as bright. Finally, the eventual ending state of our sun, which we'll talk about later, are white dwarfs. These are going to be very dim and very hot. So notice they are hot, they're over to the left of the diagram, but they're down at the bottom. And because they're so small, they're still going to be very, very dim. So these are hot, dim stars. Okay, everybody, that does it for the first 3 pages of notes. So what I'm going to do now is I'm going to stop my screen sharing, and I'm going to ask you all the first 10 questions. And locked mode is not enabled. So at any point you'd like, you can pause this video and then find the answer and answer in Google Classroom. In Google Classroom, you will only see the multiple choice answers, so you have to actually listen to the words coming out of my mouth for the questions. Okay, question number 1. What is a large ball of glowing gas hot enough to begin nuclear fusion? Question number 1. Feel free to pause the video as I take a sip of coffee from my NASA mug. Lydia, don't swing too high on the swings, honey. Don't get hurt. Question number 2. This catalyst of the universe powers the interiors of stars and gives us life. Question number 2. Question 3. Every second of every day, stars like our sun fuse together 2 atoms of blank, atomic number 1, to make 1 atom of blank, atomic number 2. Fill in the blanks for question number 3. Question 4. What physical property of stars directly relates to temperature? So for an example, because our sun is 6,000 degrees Celsius, we know that it must be what? Question 4. Okay, let's talk about brightness. Question 5. When you go outside at night and stare upwards at the stars as they appear at different distances from the Earth, what type of magnitude are you observing? Question number 5. Question 6. Average to low mass stars like our sun will not create very heavy elements within their lifetimes. In fact, they only fuse up to the element blank. Question number 6. Question 7. The Hertzsprung-Russell diagram is legit. What star group snakes through the entire diagram from the upper right corner to the lower left corner? Question 7. Lydia, where are Cami and Violet? Are they out there? Okay, don't make a mess in the sandbox. Question 8. Speaking of the HR diagram, what properties would stars in the lower left corner of the diagram have? Lower left corner. Question 8. Number 9. Bright and cool. This star group is found nestled at the right of the diagram, immediately below the red supergiants. Name that star group. Question 9. And finally, question 10. Rare but highly visible in our sky due to their size and brightness, these stars found in the upper left corner of the diagram are very hot and blue. Question 10. All right, Astro Teens, that just about does it for lecture number 1 of 3 lectures for our section on stars and galaxies. So if you haven't done so, please head to Google Classroom and answer questions 1 through 10. They're all multiple choice. I think they're pretty easy. Thank you so much for tuning in, and tune in next time for lecture number 2. From everybody here, it's Mr. Krug. Peace.